All right. I see it is time from my side. Good afternoon, or good morning, good evening, or good night. Welcome to the Topology Optimization webinar. Today we have a very interesting session on topology optimization for batteries. It is very kindly organized by Professor Xiaoping from the University of Wisconsin-Madison. And Xiaoping, thank you for organizing the session. Please take it from here.
Okay, Jing, thank you. So let me share screen. Can you all see my screen?
Yes.
Okay, thanks, Jing, for inviting us to organize a webinar, and welcome to the 34th top webinar. So my student and I discussed what we'll be talking about. We decided to talk about topology optimization for batteries. So here's the schedule. First, I will give a very gentle introduction to topology optimization for batteries. We will then have three featured speakers, Professor Shinji Nishiwaki and his PhD student from Kyoto University, Japan. Professor Nishiwaki is actually professor in mechanical engineering at the Kyoto University, working on structural optimization and topology optimization. Our next featured speaker is Thomas Roy. He's a staff scientist working in Lawrence Livermore National Lab. He's currently working on electrochemical applications, working on solver development as well as topology optimization. Our third featured speaker is Professor Adriano Sciacovelli. He's a leading expert in thermal energy storage. So our plan is we will go through the full presentation first. If you have questions during the presentation, you can type your question in the chat room. Afterwards, we hope to have 15 minutes for Q&A. With that, I would like to go to my brief introduction on topology optimization for battery, with the hope of setting up the context for the three featured speakers. So here's my general introduction of topology optimization. Topology optimization is really optimizing material distribution with mathematical programming. For example, if we have a structured domain, how should we design material distribution so that the structure is the stiffest or the compliance is minimized? As you can see, the topology optimization does not assume any preconceived shape or size. The geometry evolution is fully driven by physics. Here, physics really cast as partial differential equations. So we essentially optimize material distribution under PDE constraint. The topology optimization by now has been well developed. Originated in structural domain, now it's being applied in many physics problems, from fluid dynamics to electromagnetics or wave propagation. Textbook has been written and multiple review papers have been written on this one. So today we thought how we can extend topology optimization to batteries. So first I will briefly explain why we are interested in batteries. Battery is really an essential enabler for modern technology. Think about from all the portable devices, cell phone, watch, smartphone, watch, game player, as well as energy storage. For example, you have this sustainable solar energy, wind energy. How do you retrieve energy when there's no sunlight or when there's no wind blowing? So battery plays a critical role, as well as in electric vehicles where battery used to power transportation. So battery has also become key technology for sustainability and decarbonization for reducing gas emission. It's fair to say improving battery efficiency, capacity, and sustainability has become a global priority. So in that context, what is the connection between battery and the topology optimizations? So here we view battery as an energy storage device that can store and release electricity. Given topology optimization is such a powerful design method, it is not surprising it has been used in battery as well. We can briefly classify the use of TO for battery into two types. One is the use TO for supportive battery components, such as how do you optimize housings to reduce mass, increase rigidity? How do you optimize structural components? How do you optimize interconnector bus or current collectors? As well as how do you manage the thermal management, for example, reducing the heat or increasing heat dissipation for the cooling plate design, or even consider how do you design thermomechanical part to increase the safety, reduce, avoiding the thermal runaway, etc. The second part is actually we call essential battery components that really deal with storing or releasing energy or charging, discharging. In that context, today we were looking at two types of battery. One is electrochemical battery. So you have energy conversion between electricity and chemical energy, as well as electrothermal batteries. You will have energy conversion between electricity and thermal energy we call Carnot batteries. So with that, let me briefly introduce the electrochemical battery. So during the discharging process, you have the electron absorbed by cathode and released in the anode, and the ion is moving from anode toward electrolyte. During the charging process, the opposite is happening. So usually design objective for such battery including how do you increase energy density, how do you fast charging, reducing cost, improving life, reducing degradation, improving safety, etc. In that context, our first two feature speakers really focus on lithium ion-based electrolyte batteries. So here, battery, we want to maximize stored energy, reducing the ohmic loss. The energy actually is a function of species concentration or concentration gradient. It also depends on the electrical or ionic potential. That is actually governed by the PDE, lithium transport equation, where the electrochemical reaction model is by the Butler-Volmer equation. For the potential, electric potential of ionic potential, we have charge equation. So within this PDE, essentially we can maximize stored energy, ohmic loss. So Thomas will be talking about liquid electrolyte design and electrode. And our first speaker, Professor Shinji, will be talking about solid state electrolyte as well as active material, the material distribution. He's looking at microstructure level. Now, this electrolyte, besides can be optimized for maximized storage, people have also thinking of using for additional function, which is bare structural load. So that's what we call multifunctional structural battery. For example, here, electrolyte, you have two phases, strong phase that has high stiffness but low ionic conductivity. You have soft phase, has high ionic conductivity but low stiffness. So how can you optimize both for multifunctionalities? So people have integrated linear elasticity into this optimization. Now, in this particular case, Lee actually using reduced order resistor network to model electrochemical equations. And this has later been extended by Raza and Najafi, where they consider temperature constraint. So they couple electrochemical elasticity and the thermal equations. They formulate as multi-objective function to maximize stiffness and maximize stored energy in terms of ionic conductivity. So besides lithium-ion battery, we can also have the fluid electrolyte, in this case called redox flow battery. So here the reaction is in the form of vanadium, for example. The reactant is transported by fluid. The reaction actually happens in electrode. So how can we maximize the reaction? And that depends on the transport of the reactant from fluid to the electrode. And how do you control the reactant concentration? And that basic electron flow is governed by Navier-Stokes equation with Brückmann penalty. And with species transportation is governed by a vacuum diffusion equation. If we're interested in the ohmic loss, so again, we have electrostatic equation, this Poisson equation for electropotential. So here, Yaji, etc., optimized this redox flow battery. Here you can see the black one is the actual flow channel. The green one is the electrode shape. So, and Lee et al. Optimized both reducing pumping power, because you have to pumping the electrolyte fluid, reducing pumping power and reducing ohmic loss, which is essentially a function of fluid velocity, pressure, or the current, the electrical potential. Here is the solid part, electrical part, and here the colored part is the fluid channel. So these are redox flow batteries. Now, that's electrochemical reaction batteries. Now we can also talk about our third speaker. We'll talk about electrothermal batteries or Carnot battery. Here, the electricity convert to thermal energy. So thermal energy storage device will be used. We can use this latent heat. We're using phase change, releasing latent heat, or we can using electrochemical reaction where the heat is released here involve vapor transport. So here we have material distribution issues. Again, for example, you can use highly conductive material in the PCM to increase this charging time, and that basically phase change is show up in the momentum equation as well as energy equation. We can also using porous, this TCM thermochemical material in fluid channel is transport and momentum equation. There we can calculate state and use to optimize the reaction. So in summary, we discuss a variety of batteries, whether it's lithium-ion battery, whether it's structural battery, or the fuel cell redox flow battery or Carnot battery. So we always want to optimize battery performance in terms of stored energy, reducing ohmic loss, or we can increase stiffness. All this battery performance is characterized by the state variables, and these state variables actually describe the governing physics equation. In the end, we solve multi-physics problem, depend on structure, depends on the type of battery we have. So that is my 10 minutes, very brief, gentle introduction on batteries. With that, I would like to transfer to our next speaker, Professor from Kyoto University.
Okay, Professor, thank you very much for your introduction. Can I start my presentation?
Yes, please.
Let me first share my file. Let me switch to the presentation mode. Can you see my file?
Yes.
I would like to talk about our research topic, topology optimization for all solid-state batteries using the homogenization method. This is a joint work with my colleague Naoyuki and Kozo and Masashi and Kazuhiro, Hiroshi, Iwai, and me. And in this presentation, first I explain the background and objective, and later Naoyuki explain the details. Okay, and all solid-state batteries are very well known. And the feature is electrolyte battery is solid compared with the regular lithium type batteries. And we have 4 advantages against the liquid-based batteries. It's safety, high charging performance, high capacity, and long lifespan. And many industries, especially the automotive industry, are very expecting to use such all-solid batteries. Especially in the BEM, battery EV or hybrid EM. Also, we can use such all-solid battery in the mobile phone. The mechanism of the all-solid battery is composed of three things: in the anode, electrolyte, and cathode. And the electrolyte is working for carrying the lithium ion, and active material is carrying an electron and maintaining the lithium. And the drawback of the all-solid battery is insufficient contact area compared with the liquid-based type of that. So we need to improve the performance by solving such kind of problem. To do that, we need to design the microstructure of such a solid-based type of the anode and the cathode. Here, we consider topology optimization method to improve the potential to provide the optimized material distribution configuration. And our goal is we construct a topology optimization method for microstructure design of all solid batteries using the homogenization method. The main novelty of our research, also this is a very, very basic research work. And our novelty is concerning time scale in topology optimization problem for battery and deriving sensitivity based on the continuous adjoint method for all solid batteries. From here, Naoyuki will explain the details.
Okay, let's switch screen. Okay, so from here, Ishida explained the methodology. Yes. So as Professor explained, our target is to optimize the mix, to obtain the mixed configuration of composite region. And this study, for simplicity, this study focus only in the composite anode, and using the homogenization approach, we define the unit cell like this, and this unit cell is assumed to aligned periodically, and so we define the design variables within the unit cell. So rho equal 1 means active material, and rho equal 0 means the electrolyte materials. Of course, we need to consider, we had better consider to the void region, but for simplicity, we neglect void. And periodical, for the design variable rho, we apply the periodic boundary conditions. So here is the governing equation for ASSBS and for macro structure, macro governing equation. So 5 design variables should be defined to solve ASSBS. So first 2 variable is the concentration of lithium in the active material. So for each region, and phi S1 and phi S2 is the electric potential in the active material. So we need to define two. We define 2 regions, and last one is the electrical potential in the electrolyte material. So electrolyte material is defined, distributed in the whole region. So only for phi E should be defined in the whole region. And J lithium, this J and eta is exchange current density and over voltage respectively. So right equation is the governing equation. So as you can see, there are 5 diffusion equations, and it has only for the lithium concentration equation, it has time differential term, and all diffusion equation has source term J, and J is a function of eta. This equation is called Butler-Volmer equation, which means magnitude of electrical reaction, and eta is a function of whole variables. So it means that this equation is strongly coupled with nonlinear equation, and it has time differential time. So following the conventional topology optimization method, we relate the effective material property to the design variables, in this case rho. So we pick up the diffusion equation, diffusion term, but this term now this term is scalar, but using the homogenization method, yes, we treat this term as tensor. So we consider as anisotropic. We treat the diffusion as anisotropic, and I explain how to derive this term. This is very simple. So in the unit cell, we solve the characteristic governing equation, and by using this one, we can calculate the homogenized diffusion coefficient. Yes. So next is topology optimization problem. So we define the objective function J as the average of the norm of lithium concentration gradient. So the idea behind the objective function is that the uniform reaction within the battery leads to higher ASSBS efficiency. This is the idea. So, and we define the volume constraint, equal volume constraint. This is due to the need for setting the condition equal. Yes. And here we derive the sensitivity for defined optimization problem using the adjoint continuous Lagrange method. Of course, we know we have odd sensitivity based on discretization, discrete form, but we don't know how to implement. So we derive the sensitivity by ourselves in continuous form, and the detail is written the detail is very long. So please read our paper. I wrote the detail, and we update the design variable using the reaction diffusion equation based on the derived sensitivity. So here is the implementation details. So the key point is that we solve the governing equation from 0 to T max, and I also solve the adjoint equation from T max to T0 in the reverse direction. Yes, and I update the design variable using the console. Yeah, so I briefly explain the numerical example. So in this case, I said I consider the graphite carbon as the anode, and lithium cobaltite oxide as the cathode. And here is the material property. I said the temperature is constant, and I said the volume fraction, target volume fraction is 0.3. And this is here, these are the mesh. And I check the derived sensitivity by compare with finite numerical difference. So I set the design variable like this, and I plot the numerical difference and the derived sensitivity. So as you can see, their plot are matched. So we think the derived sensitivity is correct. And here is the obtained result. So red part means the active material, and blue part means the electrolyte. And here is a microstructure distribution, and here is a macrostructure image. As you can see, the result is very simple, horizontal material distribution. So this is very simple, but very reasonable, because as you can see, this history plots the lithium history as the optimized structure. So lithium ion and electrolyte want to move the horizontal axis. So it means the material should be distributed in horizontal to reduce the transport energy. Yes.
So
Naoyuki, if
I think your presentation going very well. The result is very interesting. Just so you know, we only have 1 minute. Keep that in mind. If you
okay.
Can. Thank you.
Sorry, this is last slide. Sorry. Yes, that's all. We had better finish. So we can separate the unit cell to 2, and we can obtain the each unit cell material distribution. So that's all. Thank you. Thank you, Professor.
Thank you for the exciting presentation. If you have any questions, you can type in the chat room, and then we will answer that after all the presentations. Thanks. Our next speaker will be Dr. Thomas Roy. and he is a staff scientist with Lawrence Livermore National Lab.
Hello. Good morning from California.
Good
Bright and
morning.
early. So I'll be quick because we only have 10 minutes. So this is work done with several colleagues here. I listed Hanyu Li, who is the first author on the second paper I'm going to talk about, which is for most of the talk. So the idea that behind this work is to optimize the shape of porous electrodes. So porous electrodes are typically just a bunch of fibers or felt or something like that. That's not very it's not very easy to engineer it. You maybe vary the thickness, or you can compress it, make it denser. You can't really shape it, but because of additive manufacturing, there's all sorts of technique to now print these electrodes at sometimes very small length scales. Like you can resolve 10 microns if depending on the technique. And so we have techniques at the lab to actually make these three on the left are all electrodes made at the lab using various techniques. So lattices or engineering actually the shape of macropores, and then this top one here is like a metal electrode. So if we can shape these electrodes, what is the ideal shape? So that's what topology optimization should answer. So in this first paper, we looked at optimizing a half cell, so just a single electrode, and we assume constant concentration. So we are only looking at potential distributions, the electronic potential, so the electrons, and the ionic potential, and they're coupled through this nonlinear reaction you saw in the previous talk, this Butler-Volmer equation. And so we just need to define piecewise defined quantities. So porosity in the electrolyte is going to be 1, porosity in the porous electrode is going to be 0.5 or something like that. So you define it piecewise with an interpolation using your design variable. And then in terms of penalization, we did porosity to the 3 halves like this. This is actually just the Brueggemann correlation, which is used in diffusion through porous media. And it turns out this is a very decent penalization. So we don't even need to change the physical equations, and it works as a decent penalization. You'll see in the next talk, we changed that a little bit. And then for the specific surface area, there's no reaction in the electrolyte phase, so 0, and then it's equal to A0 in the porous material. So we apply a current at the half cell interface, so at the top, gamma 2, and then we fix the electronic potential at 0 at the current collector. And so the shapes we get will depend on the physical parameters we do. So we did a bunch of a sweep through different dimensionless parameters, and in this case, this is like one of the, or I think maybe this one is not 6%. This may be a mistake. But you can see if you make it, if it's a high effective ionic conductivity, so if there's no trouble with ions diffusing through the electrode, then you get a small improvement, and you get these big features because you don't need small features. And if you move to this modified Brueggemann correlation with very slow ionic conductivity inside the solid, you'll start getting all sorts of I guess macropores that facilitate the transport, and then you get like a 6-time improvement. This is using the most extreme value we could find in the literature. What is the objective? So I'm saying improvement. The objective is literally this very simple expression at the top, which means because we fix the electric potential, this minimizes the cell over potential. So for a fixed current, we're minimizing the voltage. So this is making a more efficient cell because there's no time dependence. We can't really track energy stored here. So it's just efficiency of the cell. And then here's a 3D version of the bottom left 2D design. Okay, so now we wanted to see what can we do full cell design. So this is a whole rabbit hole that led to this paper. Let's do full cell now, optimize both cathode and anode at the same time. But we also want to make the model more complicated, so we introduced the ionic concentration. So this is defined as a salt concentration. So there's let's say you have some electrolyte concentration. This is the salt that is dissolved in there. So the lithium salt that you have in there. So there is migration of the ions due to the ionic potential, but it's written in this weird way because we chose the salt concentration. This is like the classic battery model where you ignore diffusion inside particles. And we also wanted to look at supercapacitive storage. So we have two reaction terms, redox and double layer capacitance. I'm not going to go through all these details, but yeah, these are two types of storage. Redox is like for pure battery, and then capacitive would be for pure capacitor, supercapacitor. If you have both, then you're a supercapacitor. So you're both, you might have high power and decent energy storage if you have both these quantities. In terms of the objective, now we want to look at energy storage. So we look at this kinetic energy term at the top right, Qian. So this is the current times voltage. So this is the energy, so integrated over space and time. And this is what we want. We want Qian, but if I'm only optimizing this kinetic energy, I'm not benefiting from the penalization of I'm not benefiting from the penalization of the ohmic losses. So we wrote it in this combination. So we know that energy only goes to the kinetic energy or the ohmic loss. So we wrote it in this way: half kinetic energy plus half energy input minus half energy ohmic losses. So we can benefit from both penalizing ohmic losses and penalizing the energy stored. So the energy stored is penalized where we have a rho to the 3 in the objective, so that the energy stored in the intermediate material is lower, and then for the ohmic losses, we make diffusion and conductivity with this 1.5 inside the forward PD, so that the ohmic loss calculation overestimates the ohmic losses in intermediate material. So you can see the plots here. So these are all very physics-specific penalization schemes that we had to figure out, and then combining both inside this combined objective. We also had to track the electrodes. So you could do this using, let's say, two design variables, like a three-field approach, but instead we use this continuous boundary propagation method because our electrodes are fixed to current collectors. So we just solve this simple diffusion problem, and that gives us where the electrodes are. So applying some kind of heaviside function to that, we can get indicators of if we're in the anode region or the cathode region. And we also want to make sure the electrodes don't touch. So we added this short circuit indicator penalization, where we track where this beta transitions from 0 to 1, and we want to make sure that happens when the density is 0. So in the gap between the electrodes. So we had to iterate a lot to figure out what a good penalization was, but when you're doing dimensionless optimization, it helps a lot because the weight here for all the cases in our paper is 1, so we don't have to tweak that weight, at least in this paper. So with all this, we can get cool 3D designs. I'm just showing the 3D ones. We did a lot of 2D designs. So we have 2 electrodes that are you can see they're interdigitated, but in the 3D case, they're also interlocked. So you can see these arches. The materials here are symmetric, so the electrodes the optimized electrodes are symmetric. And you can see there's arches, they're actually interlocking here. So this is something you cannot get using just 2D. And this is similar to some other studies that people are doing, like at UC Santa Cruz and at Livermore, looking at interlocked electrodes. So it was nice to see this from the topology optimization as well. Yeah, here's a little video of one of the electrodes. So right now what we're doing is actually turning this into full battery optimization. So considering diffusion inside the particles. So this is now a pseudo 4D model. So at every point in space, you consider a spherical particle. Makes it a bit more expensive. And we have all sorts of other activities like shape optimization and plans for the future, like coupling this to structural optimization. You can find the code for the first paper on GitHub. It's been open source. All right, that's it for me.
Thank you, Thomas, for that exciting talk. So now we turn to our third speaker, Professor Adriano Sciacovelli.
Sure, let me share my screen. And yeah, first of all, thanks for the invitation. My pleasure to give exposure also to another area in energy storage, particularly on energy storage technology that are primarily heat-driven. So we come from this space of thermofluid sciences, particularly for the development of energy storage, thermal energy storage. And let's say topological optimization methods are one of the several tools in our toolbox to be inspired on how to improve and enhance performance of thermal energy storage. And that's our kind of overarching goal and activity, which is, let's say, driven by the fact that vast majority of end use of energy is in the form of heating and cooling. Just to give you an idea from a UK perspective, this is a chart from one of my colleagues. What you see in blue is aggregated demand for gas in the UK, which is primarily used for heating purposes, either in buildings or to some extent in industrial processes, while electricity and electrical usage is this wiggling, let's say, curve in red. So we look at, as you imply from my title, in pure thermal energy storage technology to store heat and mitigate these intermittencies at various timescales, from, let's say, daily intermittencies to potentially long duration intermittencies, like seasonal. Standalone as well as combined with conversion back and forth from electricity. One of the main drivers here is electrification of heat. So the work that I'm presenting here is primarily from the first category, is energy storage, thermal energy storage on its own, but fits also the purpose of what sometimes are called Carnot batteries. What we have been working primarily are on these advanced thermal energy storage, let's say, categories, so-called latent heat thermal energy storage and thermochemical energy storage. The space of options for thermal energy storage is quite broad and vast. Latent heat relies on so-called phase change materials, exploiting solidification and melting processes as a way to store thermal energy, and we work on these over the last few years, and more recently, or in recent years, more on thermochemical energy storage. So also here, this is a category that can be split in multiple subcategories, but the key underpinning principle is use of or exploit of reversible reactions driven by heat as a way to store thermal energy. So if we imagine, let's say, a generic thermochemical reactions with the enthalpy of reaction delta HR, during charging process, the heat is provided to, let's say, or is supplied to the reaction and the underpinning material as a way to store heat and produce two subproducts, A and B, which, as long as, at least, let's say, from theoretical point of view, are kept separately, they essentially store heat in the form of chemical energy. And when they are recombined together, they release the previously stored heat. This is from, let's say, theoretical point of view. One of the advantages is that we have relatively large energy storage densities and potentially long duration of storage. We have the opportunity to exploit reversible chemical reactions and therefore use avoid, let's say, standby losses that are affecting latent and sensible thermal energy. So at a fundamental level, the, let's say, issues in terms of exploiting this potential are in combining heat and mass transport processes. What you see here at the center from the literature is how a thermochemical storage material look like. This is strontium bromide, and the challenges typically underpinned by low thermal conductivities of this material, as well, usually low porosity of this bed, which essentially slows down transfer of heat and of mass, particularly of the sorbate that is in contact with this material that triggers the reaction. In this case, it's a reversible reaction between strontium bromide and water vapor. So the approach and the interest that we have is to let's say, minimize or mitigate these performance issues through design of heat exchanger components that interacts with these materials. So very similar to a previous speaker, our design variable is the distribution of the heat exchanger material in this archetype of thermochemical storage reactor. So the actual metallic interface that is between the reactive material, let's say in white, and the carrier of energy, a working fluid that, for example, can deliver heat to the end users, like domestic end users or industrial process. Importantly, and a bit differently from the previous presentations on electrochemical storage, one of the other key, let's say, performance parameters here is the temperature at which the heat is stored and retrieved, or in other words, sometimes called also the exergetic content of the heat stored. So the quality at which this heat is stored is quite important, and it's not only about extracting and storing heat effectively, but also extracting and storing heat at the right temperature that allows better end use of that heat. So as you can imagine from this slide, we looked at, in this case, at two-dimensional topological engineering of these surfaces with the intent to maximize the performance, in particular the energy stored, effective energy storage, which I will comment in a second. Our problem is a multi-physics problem that involves mass transport and energy transport. Mass transport is the sorbate, so in this case, this water vapor that permeates or that is transported through the thermochemical storage material, strontium bromide, the corresponding transfer of energy, and very important, which is a part that relates more to material aspect, the formulation of the reaction rates, how the kinetics of this material is described. What is here highlighted with these boxes are the thermophysical properties and parameters that becomes design dependent when included in a topological optimization framework. So the diffusivity, the porosity of the let's say material, as well as the thermal diffusivity, as well as the reaction rate, because obviously where there is let's say thermochemical storage material, we have a reaction rate potentially different from zero, and where instead we have a heat exchanger material, obviously there is no reactivity taking place. For performance indicators, as I mentioned, what we are interested in or we typically pursue are two paths. One is material, what we call material utilization maximization. So this means the total amount of energy that can be retrieved from the thermal storage system for a given certain amount of time and for a certain amount of volume dedicated to the heat exchanger. And on energy output maximization, where we actually only constrains the total volume occupied by both the material and the heat exchanger. And we look at effective energy storage density, which means that is the energy retrieved above also a certain temperature threshold because of the quality of the thermal energy. We benchmark against the traditional, let's say, heat exchanger designs that have been used typically against, or in this space, which comes from very, let's say, traditional heat exchanger designs used in process industry. So finite tubes, either longitudinal finite tubes or transversal finite tubes. And what you see here on the right-hand side for a prescribed discharge time of 1 hour is the effective energy storage or energy retrieved per unit of volume for the benchmark case and the topologically engineered case, where the energy output maximization leads to the structure that extends far deeper into the reactor cross-section, while the maximization of material utilization focuses on essentially maximizing and extracting the net effect use of the material that is more close to the proximity of the central pipeline that transfer the heat to the potential end users or to the source that charges the thermal storage. We have looked at various, let's say, parametric sweeps, the discharge time, and how the geometries and the topological engineered geometries are affected by these effects, as well as other parameters. For example, the porosity of the bed, the nominal porosity of the bed and the material, as well as other dimensions of the heat exchanger itself. So, for example, the nominal energy storage capacity of the entire device. I'll spend the last a minute indeed to comment on the porosity aspects. So one of the key challenges that typically after a few cycles of these reactors, there is agglomeration of the material, which translates essentially in an effective porosity that diminishes over time. So we looked at how this can be mitigated with heat exchanger design can, let's say, mitigate this reduction of porosity and therefore more difficult transport of the sorbate through the reactor. So we try to optimize, obviously, for an entire history potentially of utilization of the thermochemical storage reactor. So this is bring me to the end. So we look at being inspired by topological engineering methods to enhance performance of traditional configuration for thermochemical storage systems. Led some insights about how to distribute the heat exchanger material, and also to necessarily not maximize only the reactive material amount, but co-maximize the presence of the heat exchanger and the material. And hopefully we are looking at how this can advance in general the thermochemical storage technologies with demonstration and testing at component scale, which are ultimately quite essential to bring these to applications in real environments. Thank you very much, and I'm looking forward for any potential questions. Thank you.
Great, Adriano, thank you. Now we are open to questions. You can raise your hand or ask in the chat room. So we have a question from Jing. This is to Thomas. Can you comment on manufacturing constraints such as shrinkage and warpage? Does the error in shape affect the battery performance?
That's a very good point. I'm actually trying to write a proposal on this to model the warpage and shrinkage. So how the experimentalists deal with this is basically trial and error. So you'll give them a part, and they'll know, let's say it's so the weird shapes are printed often using stereolithography. So it's basically like shooting a light, and then you get this shape of a polymer, but you don't want that. You want something conductive. So they burn it, and it shrinks by like 40-50% or something like that. So they really have to work hard to control the shrinkage. So it's all dealt with at the lab at the moment. In the lab, and then they'll have to realize, okay, well, it's too small. Let's print a little bigger. It's all ad hoc. It's all trial and error. And yeah, one thing I'm interested in is like, okay, so if we can account for shrinkage and non-uniform shrinkage in some kind of thermoelastic model, can we then provide the green body that will eventually lead to the optimized design that we want? So this would be another model we could add to the Ford problem in the optimization. But yeah, it's all taken care of at the lab. And in terms of length scale control, then we use the typical filters and thresholding and things like that. So
great. Thomas, can you comment on? You also mentioned you plan to apply shape optimization.
Yeah, so we've already done this using the simple two potential model from the first paper. So we have our inbuilt in-house finite element code, and they do shape optimization. So we've done shape optimization using just moving the nodes but we also have a level set optimization. So there should be a paper at some point about comparing topology optimization and shape optimization for porous electrodes.
Great, looking forward to it. Any other question from the audience? While we're waiting for the question, I have a question for the first speakers. Professor Nishiwaki, you talked about this microstructure design using homogenization. What is the manufacturing method do you envision that will be able to make your design?
Thank you for your question. Probably Naoyuki will give an answer.
So actually, so maybe we need to use the 3D printer to make the battery. I saw the news in the US. It has a company to make the composite material of battery to make using the 3D printer. So I hope we can merge that technology. Yes.
So, okay, so you hope some 3D printing technology will be able to make your design. Okay.
Yes.
Great.
I think
Thank you.
once we can propose a very high performance structure, some auto company may develop a way to manufacture such a structure. They are very, very interested in the high performance structure.
I see. You're saying if you have the performance is very good, then company will be able to manufacture them.
Yeah, I really hope so.
Got it. Thank you. My next question is to Adriana. Your thermochemical material optimization is very interesting, but I saw the design is mostly 2D. Is that because of computational cost, or is that because of manufacturability constraints?
Yeah, great question. So, as I mentioned at the beginning, we came with an angle of being quite focused on the implications down the line with the technology adoptions, manufacturing, and development. So we looked quite a bit in extrusion manufacturing methods, which are relatively cheap. So the cost is primarily allocated into the die, and the shape of the die can be relatively flexibly made. And that's why we look for these heat exchanger structures as outputs of an extrusion process.
That's
right. That's
right.
why we have looked primarily in a 2D optimization. For the latent heat system, latent heat thermal energy storage system, which I haven't presented here, we did some time ago an attempt to do 3D optimization or design more accurately. And we see that with retaining only 2D features or 2D design, we lose approximately 15%, 20% of the performance improvements. But we still have a good, let's say, enhancement compared to off-the-shelf traditional heat exchanger designs, which from let's say, manufacturing or adoption of designs from, let's say, equipment manufacturers is still beneficial.
Oh, that's good to know. So for the ease of manufacturing.
Yeah.
So great. So it's your technology will be more readily to be adopted by the industry. That's fantastic.
Yeah, I think maybe there is an element to comment here on the nuances of the thermal storage, let's say, technology, which, let's say, the industry hinges on less sophisticated manufacturing methods compared, let's say, to batteries, etc. And hence also that has some implication in how to approach it from the very beginning from our optimization point of view.
Sure, that makes sense. Thank you. And our next question is to Naoyuki.
Oh, yes.
Why is the optimized microstructure simple like a bar shape?
Yes, that's a good question. So the reason why is we introduced the homogenization method to represent the microstructure effect to the macrostructure. So, and as we know, the homogenization method extracts only the diffusion term. So, so diffusion phenomena dominant in the optimized structure. So results become very simple. That's my understanding. Yes,
Great. Any other questions?
I have a question. So for this first talk, the objective function is the uniformity of concentration, which is something you know is going to be useful, but it's not like it's not the primary thing you care about, right? What you care about is performance, efficiency, energy stored, or whatever. So is there not a way to define an objective that is what you actually care about, and then hopefully the optimizer will make the concentration uniform because that's beneficial. So in our case, like that's what we observe. Like if you have like something like energy stored, you actually calculating your energy stored, then the optimizer will end up doing what you think is beneficial, but it might not be it's not the only thing it cares about. There's other things than just let's say the uniformity of the concentration. So it will find trade-offs that are implicit, right? So I don't know, do you have is there no way to implement a more primal objective? You understand my question?
No,
Right.
do you understand? No,
Is it-
do you understand his question?
Sorry, sorry.
Was
So,
that
like,
about
uniformity
uniformity
of
of concentration? Go ahead.
Uniformity of concentration is like it's something that you think is going to be useful, but it's not actually something that is like it doesn't give you any. It's not what you're measuring in terms of performance of your device, right? So someone an experimentalist he's going to measure capacity or energy stored or something like that, power. Whereas the uniformity of concentration is sort of a derivative, like it's something we think is useful, but it's not like it's like secondary.
Yes. So maybe I try to answer. So as you said, so uniform. Our result is we consider only one unit cell, so the result is uniform. As you said, the topology optimization advantage is we can consider the ununiform the material distribution, and we already tried the macro scale material distribution optimization, and I'm writing the paper. So as you said, ununiformed material distribution can exhibit the good result more than uniform distribution. Is this correct? Sorry.
I was talking about your objective function, which is like
Objective function.
Yeah, grad C, which is the uniformity of the concentration.
Sorry. Okay, sorry.
Like, are you considering
yes,
other objective functions that are maybe more practical or like, I don't know, more
yes, that's
primary?
yes.
Yeah.
So actually,
this is dragging on too long, but we can talk.
Yes. So we check
You first consider the similar objective function at the
Yes.
first step, right? And finally,
Yes.
you are using the proposed objective function.
Yes,
You had
but
better why you pick up that such objective function.
yes. So actually, I want to first. I don't know the detail of the battery at first, so we tried a lot of objective function, and I heard the over voltage is during the discharge and charge process that that area that area between the potential during the discharge and discharge to minimize that region is good, but
Yes.
I didn't know how to evaluate only discharge at that time, so I checked the if some function to has same tendency. So and that Navrasi and Navrasi is has the same tendency in the same same capacity condition. But now I understand how to derive the evaluate the over voltage only during the discharge now. So in the next research, what I do now, I using the over voltage minimization problem. Yes.
Yeah. Oh, all right. Well, that's good to know.
Yeah.
Nice.
Thank you.
Looking forward to the next paper.
Thank you.
Any final questions?
There's one question in the chat to Thomas.
Yes. I'm a bit new to topology optimization for supercapacitors and microstereolithography. I have a naive question whether simultaneous optimization of specific surface area and the electronic connectivity is possible. Additionally, I want to grasp more background on this particular subject with respect to supercapacitors and electrodes. Their fundamental papers are inflexible. Well, if you want to read about the application about supercapacitors and in porous electrode theory, you have to read the Newman textbooks and papers. And then if you want to look at topology optimization of supercapacitors and electrodes, you have to look at my papers. This. That's the only ones for porous electrode optimization like I'm doing. So it's new. Simultaneous optimization of specific surface area and the electronic connectivity. So the optimization is sort of there's an implicit trade-off between, so if you're optimizing, let's say, minimizing your overpotential or optimizing your energy stored, I'm not giving it a constraint. There is an implicit trade-off between the amount of chemical activity and transport losses. So the optimizer will figure out what is that ideal trade-off. So I'm not giving it a volumetric constraint, right? Or there's always a trade-off between, like you say, specific surface area and connectivity. So it tries to balance. If you just fill the whole domain with material, then you'll have bad transport losses, but theoretically you have more available active material. But if you dig channels into there, you'll reduce your transport losses, but and then unlock those active materials. So it also depends on how fast you're charging. Anyway,
Great.
More time.
Thanks, Thomas, and thanks for the questions. With that, I think this concludes the webinar. I want to thank all the speakers for taking time, and thanks all the participants, and thanks Jing and Niels, Matthias, for inviting us for organizing the webinar. Great.
Yeah, thank you for joining us today. Our next top webinar will be in February, and it is about vibroacoustics. Hope to see many of you there as well. Have a nice day.